Welcome back, folks. As always, we're going to start with a review. We're going to show the parallels between the direct current and alternating current. Then we are going to briefly discuss AC, Thevenin and Norton circuits, and we'll conclude by talking about the ideal transformer. There are many parallels between our DC techniques and our alternating current techniques. Our first was Ohm's law. That became a voltage vector over a current vector by an impedance vector. We also talked about pi, which becomes complex power, vector S, over voltage vector multiplied by the complex conjugate of the current. In the DC world, we often wrote power is equal to IE is equal to I squared R is equal to voltage squared divided by resistance. In the AC world, complex power is equal to voltage vector by the complex conjugate of the current vector is equal to the magnitude of current squared by impedance is also equal to the magnitude of the voltage squared divided by the complex conjugate of the impedance. I won't go into it now, but we do know that KVL and KCL absolutely hold true between both AC and DC circuits, which means our mesh and nodal techniques would also work. By the way, do you remember which one is associated with which technique? Mesh was always concerned with the loop voltages, so that's Kirchhoff's voltage law, and nodal was concerned about the currents entering and leaving a node, so that's Kirchhoff's current law. In a moment, we'll explore Thevenin and Norton and how they apply to AC. Before we get started with Thevenin, let's take a moment to do a quick power problem. Your opening move is to calculate the impedance of the reactive components. The impedance of the inductor is 2 pi f L, and the reactance of the capacitor is 1 over 2 pi f and C. Using our calculator, 2 times pi times 60 times 0.025 gives us a value of 9.42. And for the capacitor, 2 times pi times 60 times 400, 10x 10, negative 6, equals, what we've done is you just solve for that part there, but now we need to do the inversion. It gives us 6.63 ohms. At this point, we can move these upstairs. The inductor becomes J, 9.42, and the capacitor becomes negative J, 6.63. We can calculate the total impedance as J, 9.43 plus 4 in parallel with negative J, 6.63. 4 invert plus parenthesis, it's negative 6.63J invert. Remember, it must look like this in the calculator. So often folks will take this negative 1 and they'll move it inside the parentheses, which gives the incorrect answer. Anyway, equals, invert equals. So that takes care of this piece. And now to that, we're going to add 9.43J, which gives us a total impedance of 2.93 plus J, 7.66 ohms. The current is calculated with Ohm's law. That's a voltage, in this case 120 volts, divided by that impedance. Now, I already have the impedance loaded up in the calculator, so I'm going to divide by 120, which is completely backwards from what this says, but then I'm going to use the invert button, which will give me the current. In polar form, please. Gives you a current of 14.6 amps at a phase angle of negative 69 degrees. From there, you can calculate the complex power as a voltage by the complex conjugate of the current. And our voltage was 120. So that's 120 multiplied by 14.6 at a phase angle of 69. To the calculator, that's 120 times 14.6 at a phase angle of 69, which gives us a complex power of 628 plus J 1640. And that is in volt amperes. You could think of this as volts. Again, this is amps, yielding volt amperes. You can also put that into polar form. So that's 1,750 VA at a phase angle of 69 degrees. The power triangle would look like this. 1750 VA, 628, and 1640. The units here are watts, and here they are bars. We call this real power. We call this reactive power. And we call this apparent power, with the whole thing known as complex power. At one point, we talked about a power factor. Power factor is equal to the cosine of theta, which is also equal to the ratio of the real power to the complex power. So let's see if that's true. So power factor is equal to cosine of 69 degrees. So cosine 69 equals about, what is that, 36 or so %. And had you used this, you would have said the power factor is equal to 628 over 1750. So that's 628 divided by 1750 should give you about the same number. So power factor of 36%, which, all things considered, is a pretty rotten number. Ideally, or in most situations, you want a power factor that's unity, which means that it's pure resistive. Again, that's in an ideal situation, which is very difficult to meet in the real world. So typically you'll have power factors on the order of, I don't know, about 80%. Let's move on to Thevenin and Norton. Thevenin's theorem tells us that any two-terminal source that's linear, so far everything you've looked at has been linear. Our circuits have consisted of resistors, capacitors, and inductors. Perhaps later we can get into things that are not linear, such as power semiconductors. Anyway, a two-terminal source that's linear may be modeled as an ideal voltage source with a series impedance. That means it looks something like this. We can talk about a Thevenin impedance. We can talk about a Thevenin voltage. The Norton circuit is very similar, except this time we have a current source in parallel with that impedance. So we would talk about a Norton current and a Norton impedance. Terminals A and B. And of course, this is you looking into that circuit. Recall that we can transform our circuit between Thevenin and Norton. We have a few straightforward tools for that. The Thevenin impedance is equal to the Norton impedance. The Norton current is equal to the Thevenin voltage over the Thevenin impedance. And finally, the Thevenin voltage is equal to a Norton current by the Norton impedance. To see this in action, we are going to work problems side by side. We're going to have a DC problem on this side and an AC problem on this side, where each problem has the same general layout and the same steps. You do remember the steps. Remove the load, label the terminals A and B, short voltage sources, look into the circuit. What you'll see is the Thevenin resistance. In this case, you see 4 plus 2 in parallel with 6. 2 inverse plus 6 inverse equals plus 4 gives us 5.5. At this point, we turn our source back on, and we use a voltage divider for this particular problem. For not all problems, but for this problem, we can use a voltage divider because the voltage here will be the same as the voltage there. So the no-load voltage makes the voltage on the output the same as it is here. Using the voltage divider, the Thevenin voltage is equal to 6 over 2 plus 6, all multiplied by 10, giving a Thevenin voltage of 6 divided by 8 equals times 10 of 7.5 volts. When all is said and done, we redraw the circuit, and we claim that the circuit we had up above is the same as a 7.5 volt source in series with a 5.5 ohm resistor. We declare that as our Thevenin equivalent circuit. You, as an observer, cannot tell this circuit apart from the original. On the AC side, we perform the same steps. The Thevenin impedance is equal to 4 plus J2 in parallel with negative J7 gives us a Thevenin impedance of 2J invert plus parenthesis negative 7J invert equals plus 4. So that gives us a Thevenin impedance of 4 plus J 2.8 ohms. The Thevenin voltage for this problem, not all problems, but for this problem, we can use the voltage divider. And we can do that because the voltage at this point, measured A to B, is the same as at this point, measured A to B. Because there is no load, that means there's no current draw across that resistor. The voltage divider tells us that we have negative J7 over J2 minus J7. And I got in trouble here because I didn't give you a voltage. We'll let that be 120 volts, 0 degrees. And we take and we multiply against that voltage. Using the calculator, we enter that as negative 7J divided by, looks like negative 5J, gives us a value, and then we multiply that by 120. So it looks like the Thevenin voltage is simply 168 volts at a phase angle of 0 degrees. Now that the hard work is done, we can sketch our circuit as a Thevenin voltage source, in this case 168 volts at a phase angle of 0 degrees, and the impedance, which is here. That's a resistor with a value of 4 and an inductor with a value of J2.8. And looking into this circuit, you cannot tell it apart from the original. Something I'd like to point out, you'll notice how our voltage source was 120 volts. If we look at this circuit, we see that the voltage is actually higher in our Thevenin circuit. That can happen. And the reason it can happen is because you have this inductor and this capacitor. And what happens is those two will have energy flowing back and forth between them. Let's go ahead and work another example. It's time for a quick break. I'll be right back as you work those problems. Okay, puppy's all better now. Microphone on. We're ready to go. I would argue that this is a Thevenin circuit. If we were to take that and convert it into a Norton, we would have two current sources in parallel. We could then combine them to simplify this circuit. So if we do that, we end up with a current source, a resistor in parallel, so that's our Norton. And then we have this current source in parallel, and then that 3 ohm resistor. This is 5 amps. And remember, a Norton current is a Thevenin voltage divided by a Thevenin resistance, which in this case is 20 divided by 2, which gives us 10 amps. Simplifying the circuit, we end up with 15 amps, a 2 ohm resistor, and a 3 ohm resistor, and terminals A and B. This Norton circuit can be transformed back into Thevenin, and then our two resistors will be in parallel, so that would be a 5 ohm resistor. Terminals A and B. Remember that a Thevenin voltage is equal to a Norton current by a Norton resistance. In this case, that's 15 times 2, which gives you 30 volts. So there is our Thevenin equivalent circuit. Let's see if we can't do the same on the AC side. This is a Thevenin, which can be converted to a Norton. We'll now have that inductor here in this position. This is our 15 amp current source. And finally, this 5 ohm resistor. 15 amps, angle 70 degrees. And this is J4. A Norton current is equal to a Thevenin voltage over a Thevenin impedance. In this case, it's 100 angle 0 divided by J4. So our Norton current is equal to 100 divided by parenthesis 4J gives us a current of 25 amps at a phase angle of negative 90 degrees. So 25 amps, phase angle negative 90 degrees. We can add those current sources. So we already have 25 angle negative 90. We're going to add 15 at an angle of 70, which gives us a current of 12.1 amps at a phase angle of negative 64.8 degrees. With that inductor in this position and our resistor here that originally had a value of 5 ohms. This Norton piece can be transformed into Thevenin, which would give us a voltage with that inductor and resistor in series. This is J4, and that's 5 ohms. A Thevenin voltage is a Norton current by a Norton impedance. So in this case, that is 12.1 at a phase angle negative 64.8 by J4. We already have the current entered, so we're just going to multiply that by J4. Gives us a voltage of, what is that, 48.2 volts at a phase angle of 25.2 degrees. So 48.2 volts at a phase angle of 25.2 degrees. That is our Thevenin equivalent circuit. Remember, the steps were identical. It didn't matter if we were working on a DC circuit or an AC circuit. Every step we took was identical. The only difference was you had to deal with the complex numbers on the AC side. I think I've mentioned this about 47.62 times before. You really need to be good at using your calculator to solve these problems. You don't want to be in an exam for the first time trying to use your calculator. That's just not going to work. On a positive note, I do have some good news for you. We have been slugging away at these problems, these Thevenin, the AC, and Ohm's law, the power, and all of that stuff. But we have just turned a corner. And what you've just done is we have just walked into the world of transformers. We've walked into the world of electromechanical machines. And closely related to transformers are motors. Closely related to motors are generators. I hope you'll agree this is the fun part of the class. This is the part of the class where we take all of that theory that we've been working on, we take all of that abstract stuff, and we start to point to very specific things and say, that's how a transformer works. When you walk outside and you see a transformer on a power line, you can say, I know what that is, and I know how it works. And that's, I think, is a wonderful feeling. Speaking of transformers, a transformer looks something like this. This is an iron core. Onto this core, we are going to wrap many turns of wire. On this side, which we'll call the primary side, we will connect the wire to an alternating current source. We'll let that be the source voltage. On this side, which we'll call the secondary, we'll again place many turns of insulated wire. which will be connected to our electrical load. We called this the primary side, and we called this the secondary side. Here's how it works. If we run a voltage through the winding on the primary, there will be a current that flows. That current will establish magnetic flux lines that flow within the iron core. Right? So all of these flux lines are determined entirely by the current in the primary. These magnetic flux lines pass through both of the coils, so we could say that they are magnetically coupled. To keep our discussion today very short, we are just going to say no to a whole bunch of physics and math, and we'll use a very simple rule. If one side has a changing magnetic field, the other side will have a changing magnetic field. If there's a voltage developed across one coil, there will be a voltage developed across the other coil. What one does, the other will follow. Schematically, it looks something like this. We have our primary winding, we have the core, and then our secondary winding. There's our source and our load. Again, primary and secondary. Just a moment ago, we said that the primary and secondary windings were intertwined, and whatever one would do, the other would follow. That's true, but there's a ratio involved, and we call that the turns ratio. For this problem, if we have 120 volts on this side, we are going to have a voltage of 240 on this side. The turns ratio is such that 1 on this side becomes 2 on that side. So our 120 volts is doubled as it goes to the transformer, becoming 240. For your note card, be sure to write down these numbers. The number of turns in the primary divided by the number of turns of wire in the secondary is equal to the voltage in the primary over the voltage in the secondary. That is also equal to the current in the, wait for it because it's upside down, the current in the secondary over the current in the primary. We would call this the turns ratio. We would call this the voltage ratio. And I suppose you could call that the current ratio. Be careful. It's primary here, but primary downstairs when we're talking about current. So remember that current is upside down relative to everything else. We mentioned that this was an ideal transformer. In an ideal transformer, the complex power in the primary is equal to the complex power in the secondary. Let's work a few problems so we can cement these ideas. We'll let this be a 3 to 1, and we would call this a step down transformer. So we're taking the high voltage side on the primary and we're moving it to low voltage on the secondary. Volts primary over volts secondary is equal to 3 to 1. That's what this says. We know the voltage on the secondary, so that would work out to volts primary over 120. So the voltage on the primary must be 360 volts, and we'll assume that that's at an angle of 0 degrees. Consequently, if you were to put a voltmeter here in the circuit, it would read 360 volts, with the assumption that there is some voltage source out here that we haven't drawn in yet. The current in the secondary is a function of both the voltage and the impedance. So using Ohm's law, that would be 120 divided by 5 plus J2. So the current in the secondary is 120 divided by parenthesis 5 plus 2J. And polar, please. So that's 22.2 amps at a phase angle of negative 21.8 degrees. Using our ratios, we would say 3 is to 1. So this is primary here, and this is the secondary. Remember now, current's upside down, so the current in the secondary would go here as 22.2 amps at a phase angle of negative 21.3 is to the current in the primary. Solving for current, the current in the primary is, in this case, it's 22 divided by 3, which gives us 7.43 amps at a phase angle of negative 21.8. So all we've done is we've taken the voltage, which here was 360 volts, and we stepped it down. We've taken a current of 7.43 on this side at a current of negative 21.8. And on this side, that current is now 22.2 amps at a phase angle of negative 21.8. Before we leave this problem, we made a statement about the power. We said the complex power in the primary was equal to the complex power in the secondary. Let's take a moment to see if that's true. Recall that complex power is a voltage vector by the complex conjugate of the impedance. That works out that the complex power in the primary is 360 multiplied by this current. So 7.43 angle is 21.8 because we want to take the complex conjugate. So 360 by 7.43 at a phase angle of 21.8. There we go, that's better. So the complex power in the primary is 2480 plus J990. Again, that's volt amps. And in the secondary, we could say complex power in the secondary is equal to 120 multiplied by 22.2 at a phase angle of negative 21.8. Right? That voltage, that current. Complex power in the secondary is 120. I did it again. That's supposed to be a positive. Let's try it again. So 120 times parenthesis 22.2 at a phase angle of 21.8 should give us about the same number. So we'll call that 2480 plus 990 J volt amps. So within the rounding errors, looks like that's true. The complex power in the primary is equal to the complex power in the secondary. Let's take a look at another example. An example that will help us explain why we use transformers in the first place. We start with a source. Here's our first transformer. We'll let there be a resistance. We'll add a second transformer. Here's the secondary of that transformer. And we'll connect that to our load. In this case, we'll let the load be 5 kilowatts. So a pure resistive load with a voltage of 120 volts. And T1 we'll call a step-up transformer. It'll go 1 to 10. Whereas transformer 2 will be a step down. It'll go 10 to 1. So we call this step up because we're stepping up the voltage. We call this step down because we're bringing the voltage down. Our objective is to find the source voltage. So we're going to work right to left as we do this. The first thing that you can calculate is right here. Well, you're given the first thing. You know the voltage on the secondary of T2 is 120 volts. You can easily calculate the current on the secondary of T2, as that would be 5,000 divided by 120, which is 41.6 amps. And now you can move to this point. We know it's a 10 to 1, so our voltage on the primary of T2 is no longer 120, but it's going to be 1200 volts. That's the ratio. 10 is to 1, as 1200 is to 120. The current on the primary of T2 will also undergo a 10 to 1 transformation. But remember, the current is upside down relative to the turns ratio. We talked about number of turns in the primary, number of turns in the secondary, and this was the current in the secondary and the current in the primary. So while the voltage goes from 1200 to 120, the current's going to go the opposite way. The current would go from 4.16 amps to 41.8 as it goes to the transformer. This next piece is very, very, very important. And it's the one thing that helps you understand what the transformer is used for. There is a 12 ohm resistor up there. If you were to calculate the voltage on the secondary of T1, you would say that is this voltage here, which we already said was 1200 volts, plus the voltage drop across that resistor. In this case, that voltage drop is 12 by 4.16 amps. And that's just a statement of Ohm's law. You have 12 ohms, and you have 4.16 amps flowing through it. So the voltage there is 12 times 4.16. So that's the resistor voltage. It's about 50 volts plus 1200. So 1250 volts. Before we move on, I want to emphasize this point right here. That is a current. And the reason I bring it up is because this wire, this resistor, this transmission line, the transmission line has a power lost described as I squared R. If you want to minimize the loss, you have two options. You could lower the resistance, right? You could lower that resistance. But that's going to cost money because it means you need to build or use larger and larger cables. The other option, which has a more profound effect because it's a squared, is to lower the current. And how do you lower the current? You lower the current with a transformer. In this particular example, if we didn't have the transformer, we would have had to send 41.6 amps across that transmission line. That's going to be a large loss. For example, without it, it would have been 41.6 squared by 12. So 41.6 squared times 12 gives you a power loss of 21 kW. With the transformer in circuit, the power loss becomes 4.16 squared by 12, which is going to be much smaller, at only about 200 watts. I mean, just think about that. Originally, we had a 5 kilowatt load out there. If you didn't have the transformer, you would have burned 21 kilowatts. 4 times the energy that went to the load would have been burned up in the wire. With the transformer, to get that 5 kilowatts across, you only burn 200 watts. And I think you'll agree that's a pretty good deal. Anyway, back to our original problem. We had solved for the voltage at this point right here. So the voltage on the secondary of T1. We can now go back and solve for the voltage on the primary of T1. So the voltage of the primary of T1 is equal to this divided by 10. So it's 125 volts. So 1 is to 10 as 125 is to 1250. Before we end this discussion, let's cover one more thing about transformers. The question is, if you are an observer here, what do you see? Of course, you could ask that question the other way around. If you were a Thevenin observer looking in, what would you see? Right? It works both ways. Here's the answer, and you'll want to write this on your note card. Z prime, right? The impedance prime that you see looking into a transformer is the turns ratio squared by the original impedance. So if we let this be a 2 plus J5, the impedance looking in would be 4 over 1 squared by 2 plus J5. So the impedance looking in would be 2 plus 5J by 16. So looking into the circuit, we don't see 2 plus J5. Instead, we see 32 plus J80 ohms.